tardes a todos, bienvenidos a muy probablemente la última edición del coloquio por este año. Ya estamos todos cansados y bueno, juntamos fuerzas para empezar ya en febrero del año que viene. Bueno, hoy tenemos el agrado de presentar al señor Roderich Moessner, y desde, ¿cómo era el instituto? Es el Max Planck, de Dresden. Y bueno, y la presentación formal la va a hacer Karen, ya que ella tuvo la gentileza, bueno, de traer a este invitado de hoy.
Muchísimas gracias, a los organizadores por mantener este ciclo de coloquios. I'll switch to English. It's a great honor for us and a pleasure to have Professor Roderich Moessner with us. We met many years ago, but we're very happy he could come and visit our institute for the first time in the south of South America, so below the line in Natal. So you're welcome. Professor Moessner studied his undergraduate and graduate studies at Oxford University in the 90s, and then worked in Princeton, in Oxford itself again, in l'École Normale in Paris, and also in Dresden. And now he's currently the director of the Max Planck Institute for Physics of Complex Systems. So that's the institute in Dresden, where I did my postdoc there many years ago. So it's an honor to have a director of the Max Planck Institute with us. We have a lot of collaborations with that institution, so it's great to continue with these collaborations. And I just wanted to emphasize one more point, is that Professor Moessner was one of the recipients of the Europhysics Prize in 2012, together of the Condensed Matter Division of the European Physical Society, together with Santiago Grijera and other collaborators, because on their work on the prediction and on the measurement of monopoles in magnetic spin ice, which is a compound which presents these magnetic monopoles. So they exist, even if you were taught that magnetic monopoles do not exist. So congratulations, Professor Moessner, and the floor is yours. Thank you very much.
It's wonderful to be here, and this is, as Karen said, this is my first visit, and it's almost a little bit like visiting family, but I have to say there are many nice places to do physics, and this is certainly one of the nicest, so I'm very impressed by the Institute and its surroundings. Okay, so today I'm going to tell you about some work which has been keeping us busy for, since 2014 roughly, it's going to be an introduction to what happens to our concepts of thermodynamics in order once we leave equilibrium. And I'm going to do a general introduction, and in the end, we're going to end up with a system which exhibits spatio-temporal form of order. Feel free to interrupt me anytime. I structure the talk so that I can add and subtract things as we go along, so hopefully I'll not overrun for too long. Okay, so basically I'm going to introduce to you thermodynamics in many body systems and coherent quantum dynamics, mostly things that you'll know, but I'm then going to work through the various bits of the title as we go along. Okay, so let's start in the 19th century with equilibrium thermodynamics. And there are two aspects, two assumptions in equilibrium thermodynamics which are so commonplace that we hardly need to think about them, and these are called equilibration and thermalisation, and they're basically encompassed by this picture. When you see a picture like this, you expect, if you come back after, say, a couple of hours, not to be able to see this assembly again. So, in fact, the system you'd expect to reach a steady state, so that's the idea of equilibration, and the idea of thermalisation observation is that to know what the steady state is, you don't need all that much information. So basically, if I tell you the temperature at which this photograph is taken, then you can say with some confidence, when you come back after a few hours, either you'll find lots of little ice crystals, or you'll find a big puddle of water. Okay, so this holds as a matter of course, but it does not always hold. And the question why it holds and how it holds was surprisingly open until a few decades ago. But let's now move from the 18th to the 19th century, 19th to the 20th century, and talk about coherent quantum dynamics. So in some sense, coherent quantum dynamics is very simple. You write down Schrödinger's equation, and you solve it, and then you have the full information about your system. And Schrödinger's equation is a linear equation, so this all sounds pretty promising. The reason that people haven't thought about coherent quantum many-body dynamics a lot is simply that there was not much need for it. So most systems that we have in the lab, like even at low temperatures, a magnetic crystal, basically equilibrate in a few picoseconds, sometimes much longer, but many microscopic processes which destroy coherence are extremely fast. And it was only when cold atomic systems came along and many-body systems started having coherence times on which one could actually do experiments, the question became relevant of what the general features are of coherent many-body dynamics. And so minimally, one thing we should find is that thermodynamics should somehow emerge. Or rather, it would be nice if we could keep thermodynamics. And exactly how and why this happens is subtle. But here is a cartoon for how this essentially happens. And so I'm going to show you several of these plots in the course of this talk. So basically what I'm showing you is an exact numerical solution of Schrödinger's equation. I'm evaluating all eigenstates, and I'm ordering them by their energy along the x-axis. And then I'm plotting some local observables, so here some density, as a function of energy. And what you see is that the observable is actually a smooth function of energy. And this is what's known as the eigenstate thermalisation hypothesis, or eigenstate thermalisation. So the statement is, if you want to know what an observable is in an eigenstate of a many-body system, you do not need the wave function of the eigenstate. Actually, all you need is its energy. Okay? And so this basically tells you roughly what the connection to thermodynamics is. I told you in thermodynamics, you only need a small number of quantities to decide what the steady state's going to look like. So basically here, if you know the energy, you know what the observable is going to be, even without the solution of Schrödinger's equation. Okay? Okay, and so this is roughly, and so they can say a lot more details about this, but roughly this is where things stand. As we left the 20th century, we're going to ask, so we basically understand what the connection is between generic many-body systems and thermodynamics. But all of this is equilibrium. Oops. The question then is, what happens beyond equilibrium? So this little machine seems to have some pretty cool properties. So I guess it's to stop the speakers from moving too much. Okay, so what happens beyond equilibrium? So most of the world around us is out of equilibrium. So you can just look around, and if it were in equilibrium, we would be living in a soup and not in a nice wood panel room. And so I should warn you, I'm not going to tell you a generic theory of many-body systems out of equilibrium. In particular, I'll not be able to explain how coral reefs come about. But rather, in the good tradition of physics, I'm going to look for the simplest deformation away from equilibrium physics, and I'm going to ask what items of equilibrium physics are going to remain and going to remain useful in non-equilibrium physics, and what new items do we have to introduce to make sense of what happens in this setting. And the setting I'm going to look at are driven systems, and something I'm going to introduce, many-body localization. But this is basically the generalization. And so what do I mean by driven systems? So by driven systems, I specifically mean systems which are periodically driven. That is to say, the Hamiltonian is time-dependent, but it comes back to where it started from after a period, capital T. And so this is motivated in part because this is a common non-equilibrium problem. Many processes in nature are approximately periodic. And it's also, in some sense, the simplest case of a non-stationary Hamiltonian. And I'm going to ask two questions. Do there exist periodic ensembles? So is there some notion that I can define ensembles in the thermodynamic sense for even periodically driven systems? And then the separate question, is there a notion of order? So can I define order and disorder even in periodically driven systems? Okay, so periodically driven systems are also known as Floquet systems. So just to define things a little bit more clearly, so the Hamiltonian is periodic with period t, and that means if you Fourier transform it, the Fourier transform only contains frequencies commensurate with the basic driving frequency 2 pi over t. And then something that turns out to be useful, or at least that I found useful, is that you can still define a time evolution operator which takes any wave function at time 0 to any wave function at time t. This is a unitary matrix, and you can use that to define the logarithm thereof, which is called the Floquet Hamiltonian. So the main reason I find this useful is that a unitary matrix, actually like a Hermitian matrix, has a complete set of eigenstates. That is to say, what you learned in undergraduate quantum mechanics, that if you want to express a general state of a system, you can solve for the eigenstates of Schrödinger's equation and then write a general state as a linear superposition. The same thing is true for periodically driven systems. So you do not, in fact, need a stationary Hamiltonian for that. And so you can still use a lot of the intuition that you get out of linear algebra for this purpose. Okay, and so the first thing that then happens is that you can no longer have equilibration, because a system can't assume a steady state if you keep kicking it, basically. But there's still a concept which we call synchronization, which is to say that if you don't look continuously at your system, but you look stroboscopically, that is to say at the same point in the drive period, so these are always a period t apart from each other, and then you record a sequence of measurements, and if this sequence becomes time independent, we say we have a synchronized state. So this is just a simple generalization of the synchronized state to the, of the equilibrium state to a time-dependent drive, where you only look at observables stroboscopically. Okay, and then model Hamiltonians. I'm not going to, so we studied a lot of different Hamiltonians for technical reasons, not always the same ones. But basically, they all have the same properties, so it's a closed system, so there's no dissipation. We look at one-dimensional systems on a lattice, and with a finite-dimensional Hilbert space, that is to say, you can think of either, say, having a particle present or absent on each side, or you can think of a spin pointing up or down, depending on what you're most comfortable with. And the Hamiltonian contains static and time-dependent terms, and what we're interested in are general behavioral pattern of many body systems which are described by Hamiltonians like this. Okay, so we basically have, as I said, so particles with a particle density, there's a potential, the particles can hop and the particles can interact. So it's believed that this is sufficiently general to have a generic many-body system, so in this case in one dimension. Okay, and now let me introduce a couple of fundamental, perhaps, concepts that you may find useful when thinking about systems like this. And it's useful to take another system where the symmetry is replaced from continuous to discrete to give you an idea of what's going to happen. And so these are crystals. So you know space has a continuous symmetry. You can shift it by any amount and it looks the same. But in a crystal, that's no longer true. You can only shift it by discrete amounts. By Noether's theorem, a symmetry goes along with the conservation law. So for spatial translational symmetry, that's momentum conservation. And if you go from continuous space to a crystal, you lose momentum conservation, but you still have crystal momentum conservation. So the momentum is conserved modulo a reciprocal lattice vector 2 pi over a. Okay, so if you go from a continuous to a discrete symmetry, you go from a conservation law to a conservation law modulo a reciprocal lattice vector. And in the case of the driving, this happens exactly the same way. You've got continuous time translational symmetry. That's a static Hamiltonian, always looks the same. That gives you energy conservation. You now drive it, you lose energy conservation, but you still have quasi-energy conservation modulo a reciprocal lattice vector. And the reciprocal lattice vector in energy space is simply the energy omega, which corresponds to your driving frequency. So if you want to have a picture in your head, you shine a laser on something that is a periodic drive, and absorbing a photon of the laser is possible, and you gain or lose energy h bar omega. So that's roughly how this happens. And what this then means is, rather than thinking of an energy axis, which is a linear axis from minus infinity to plus infinity, it's more useful to think of a circle, because energy 0 and energy h bar omega are the same energy, right? So there's no longer a notion of high and low energy, for instance, in a driven system. You simply have the energies living on a circle. Okay. And if you have a tunable driving frequency, the radius of that circle becomes adjustable. So that's like having a crystal with a tunable lattice constant, which is, of course, technically much rarer. But if you've got a continuous frequency laser, you can simply change the radius of the circle, which is the same as changing the photon frequency of your laser. Okay. Now here comes the first central result, which we called Floquet eigenstate thermalisation. So, as I said, quasi-energy is only conserved modulo omega. And now imagine you start with your system in an eigenstate of the static Hamiltonian at low energies, and then you start shining a laser on it. So what I'm going to tell you now is a rationalization of a result, which is generally believed to be true, but we don't have a proof for this, and you should be aware of the fact that we don't, and that there may be exceptions which may be interesting. But basically, the very simplest way of describing what happens is, if you look at the density of states and you ask, am I more likely randomly to absorb a photon or to emit a photon? The answer is you're much more likely to absorb a photon, because there are many more states at higher energy than at lower energy. That's just the statement, basically, that the ground state is unique. That's the third law of thermodynamics, and there are many, many high temperature states. So then, basically, it's always more likely to absorb energy than to emit energy until you reach the maximum in the density of states. And the maximum in the density of states is essentially where you maximize the entropy, and that's something that you do in common parlance at infinite temperature. Or put differently, you absorb energy until your state has no structure left. And then you stop, because basically you've maximized the entropy, and so then you have got no correlations left. Okay, so that's a way of thinking of it in a time domain. More generally, if you do thermodynamics, you know that for each conservation law, you have a Lagrange multiplier. So for number conservation, you've got a chemical potential. For energy conservation, you've got a temperature. We lose energy conservation, therefore we lose temperature. We just maximize entropy, subject to no constraints, and that means we get complete disorder. Okay, so that's the result. So the statement of eigenstate thermalisation is, the observable is a smooth function of energy, but since the energy is quasi-periodic, there's no longer a notion of high or low quasi-energy, and the simplest way of then having a smooth function is to have a constant function. Okay, which is, again, say a constant function, and the constant function is just trivial. So if I give you a certain density of particles, every eigenstate has that density. So this is sometimes called heat death or infinite temperature average or whatever you'd like to call it, but the statement is a generic many-body system, which is periodically driven, has no non-trivial correlations. Okay, that's what we call Floquet ETH. And you may wonder, we're only 20 minutes into the talk, and I'm already telling you there's absolutely no structure to the problem. So luckily, there's a way around this, but nonetheless, it's worth remarking. So this is a generic statement. And another thing that I found very amusing, so this, I think, was published in 2014. So it's a result that anyone could have derived with even a reasonably, normal computer, I think starting from the 1970s. And it's one of the miracles that such a fundamental result was waiting until 2014 to be discovered. And when we discovered this, I spent a lot of time looking through the literature, just wondering, surely someone must have done this before. But it turned out no one had. Okay. Okay, so there we go. Generic many-body systems subject to periodic driving are boring. So what else is there? Well, I'm going to focus on one. So there are various ways you can get around this. One is you can have transient phenomena. That is to say, you can have non-trivial physics, but on a time scale which is limited. I'm not going to say anything about that. What I'm going to concentrate on is many-body localization. I'm going to introduce that on a slide and then generalize it to Floquet systems. Okay, if anyone wants to know about transient phenomena, feel free to ask, but I'm going to continue with many-body localization. So here's another eigenstate thermalization plot, observable continuous function of the energy, but there's an alternative. So this is what's known as a many-body localized system. You do the same plot, you order your eigenstates according to energy, and it's a complete mess. There's no particular correlation between neighboring sites. And so this is a system which is known as a many-body localized system. And many-body localization is a relatively young subject, just about 10 years old or 15 years old. And there are still very many fundamental open questions. The most fundamental one of them is, does many-body localization exist? So the answer may be no. So we're going to work on the assumption that it does exist. And I'm going to give you a very simple picture of many-body localization, which you can keep in mind until the rest of the talk. And I'm going to sweep all the subtleties under a rug. So here we go. So imagine you've got particles subject to a random potential. So the location of the lattice sites I'm putting up and down depending on whether they've got a high or a low random potential. And now imagine you've actually only got that random potential. So that you've effectively got a classical problem. If you just tell me where the particles sit, I can tell you what the eigenenergy is by adding up all the random potentials. Okay. And now if you do this, you can already explain this picture here, which is also known as eigenstate chaos, and that's basically the following. Imagine I change my state just a little bit and I move one particle to its neighboring site. So then the correlations don't change very much. But since the energy is different, since the potential is very large, the random potential is very large, the energy does change a lot. That is to say, if you remain very nearby in correlations, then you go a long distance in energy space. So the correlations are basically between a site here and a site a long distance away in energy. If by contrast you want to have a small energy difference, then you have to find a sequence of moves, all of which change the energy by a lot, but the sum of which changes the energy by little. That means you basically try and try and try. It's like a random walk with very large steps, and you ask, when do I get back to the origin? And you have to try a lot until you're lucky enough to land back at the origin, and trying a lot means changing a lot of degrees of freedom, which on this picture means if you want to remain nearby in energy, you go a long distance in configuration space, and therefore you change the correlations by a lot. Okay? So this is how to explain the eigenstate chaos. Now, the miracle of many-body localization is that this classical picture I've given you here is stable to the addition of any local perturbation to your Hamiltonian. So you can add potential energy, interaction energy, 2, 3, 4, 5 particle interactions, whatever you like, this picture is not going to change. Okay, and so this is what makes many-body localization at the same time very easy in this picture, but also very subtle in its stability. Okay, now here, Floquet many-body localization. So I can give you a simple picture, which again is not rigorous by any stretch of the imagination. What happens in Floquet systems? So again, here now we don't have energy, we've got the quasi-energy. We organize all the states according to their quasi-energy, and then we've got Floquet ETH, shown you here, and then there's also this eigenstate chaos of Floquet MBL. And you can then ask, and for which parameter values is many-body localization stable, and for which parameter values do you actually get Floquet ETH? Now we come back to this. So if you've got a localized system, what you, in a very loose sense, think is that if I've got a localization length, and if I perturb my system somewhere within a localization length, I'm going to see the effects of the perturbation. But if I go much further away, I no longer see the effects. So then I do this thought experiment where I cut my system into bits which are bigger than the localization length, and then not much changes because the information that I've cut them doesn't propagate through the system. And now, the important thing is that now I've got a finite size system. And now imagine I'm driving this finite size system very fast. So a finite size system has a finite energy width, so I'm basically plotting the areas of allowed energies of that system, and then I drive it with a very high frequency, which is bigger than than the bandwidth of this finite chunk of system. But then you see you can no longer absorb a photon because there's no initial and a final state, which is connected by an energy difference of the size of this photon. So in other words, when the system is localized, it can't let enough spins act coherently to absorb a very energetic photon. And therefore, the system just sits there and does nothing. And then if you decrease the driving energy, eventually you get within the single particle bandwidth, and then what happens is what I explained before, you get Floquet eigenstate thermalization. So in other words, in a driving frequency disorder plot, at very high frequencies, it's like you were not driving at all, and you've got the eigenstate thermalization, MBL transition like in the static system. But then as you lower the driving frequency, the thermal phase grows at the expense of the many-body localized phase. But the important thing is there is a Floquet many-body localized phase. Okay. Are there any questions so far? Yeah? Yes. Yeah, so it's certainly true that the heating process itself, when you get near the transition, is a nonlinear process, and therefore increasing the amplitude is also going to shift things in disfavor of the many-body localized phase. But we don't believe that something particularly qualitative happens. But since I haven't labeled the axis in any quantitative way, it doesn't make a difference. But you're right, it would change things. Yeah. Another question here? Mm-hmm. Do you mean the average energy average over a period, or so are you taking the average Hamiltonian and evaluating that in a Floquet eigenstate? Is that okay? Okay, it's constant, 0. That's right. I mean, this is Floquet eigenstate thermalization. Otherwise, you could tell them apart by the Hamiltonian. That's right. It was a little bit disappointing, but and okay. So a way of seeing this, let me just briefly say that. I'm going to explain this very quickly. So if you switch on the driving amplitude at 0 driving frequency, so you have the many-body spectrum, and then you fold it onto this radius, on this circle of radius h by omega, and then when you switch on the driving, you start mixing the levels, right? And the basic point is that the levels are exponentially narrowly spaced, so this is a little bit hard to show, but you have a huge number of level crossings. And in the end, at each level crossing, you mix the state coming from up to the state which comes from down. And by the time you've had a huge number of these crossings, you've mixed states from the entire original spectrum. That's how the average Hamiltonian being 0 comes about. You've got components from across the energy spectrum. Right. Okay. Okay, so now let's move on to order. So I first told you have Floquet ETH, so there's no order in the equilibrium sense, but you can go out of equilibrium by going to Floquet many-body localization. And I'm going to argue that in the Floquet MBL phase, you can actually have a notion of order. And this uses a concept of eigenstate order, which was formulated around the same time. So this is now getting a little bit heavier into statistical mechanics, but let me make the following statement. So if you've got a ferromagnet, you're probably aware of the fact that the eigenstates of your Hamiltonian for a finite size system aren't all spins pointing up or all spins pointing down. They're actually cat states, all spins pointing up plus all spins pointing down, or all spins pointing up minus all spins pointing down. And these cat states are split exponentially weakly in the system size. So if you have, say, an exact diagonalization of a finite size system, the way to decide whether or not you've got symmetry breaking is somewhat counterintuitively not that you look whether there are correlations of spins pointing up and spins pointing down. You actually look at the finite size splitting of this doublet. Okay? And this works in a wide variety of settings. Say even for topological order in the fractional quantum Hall effect, you're going to see a triplet because there are 3 Laughlin states which which are exponentially degenerate. So it turns out in disordered systems, you can have this kind of eigenstate order as well, but rather than just occurring in the ground state, it can actually occur in the entire energy spectrum. So in other words, you can think of generalizations of ferromagnets, which are spin glasses, where each state comes in a pair, and each pair forms a pair of Schrödinger cat states. Okay, and so the thing that we're going to look for is this eigenstate order in the spectrum, and if we've got an ordered state, we get pairs of the eigenstates which are randomly distributed, and a disordered state, we have randomly distributed energies like that. So that carries over directly to Floquet systems. The difference is that in Floquet systems, we don't have the states organized along a linear energy axis, as I said a second ago, but we have the states organized on a circle. But again, you can ask, do the states come in pairs on the circle, or do they come as individual states in the circle? So that's what we're going to look for. Okay, now this is, again, a rather indirect way of looking, or rather direct way of looking for eigenstate order, but a very indirect way of looking for order. So what we're simply going to do now is we're going to take some state, we're going to act on it with some operator, and then we're going to ask, at what energy difference is there a second state which has an overlap with a state which is thus generated? So basically, we take an eigenstate, we do something to it so that it becomes a linear superposition of many other states, and then we ask, at what energy do these other states live? And what you find as a function of quasi-energy difference here is that if you tune parameters in some Hamiltonian, which I haven't given you in any detail, that there's a regime, which we call the disordered one, where there's no particular structure in the relative energy difference between the state and the partner which we're looking at. But if you then cross a phase transition, you actually find that there's a huge preference for the second state to live at approximately the same energy as the first state. So that's precisely the eigenstate order I showed you before. In the disordered phase, there's no correlation between two energies. They're completely random. In the other case, there's huge correlations, and if I give you one energy, you know that there's a second state very nearby in energy. Okay, so this is what we know, what's known as a spin glass, as a Floquet spin glass. Okay, now here comes the surprise. You can do the same thing with this. You can do the, that's not what I wanted. You can do the same thing with a Hamiltonian. And somehow want to get rid of this little arrow. You can do the same thing with this Hamiltonian. And what you find is that there's a third phase. And in this third phase, somehow the buttons don't commute. So there is a third phase. So if anyone knows how to get rid of this cursor, that would solve the problem. If there's a third phase where the eigenstate energy difference is not zero and it's not uncorrelated, but it's actually pi. So in the picture of eigenstate order, this corresponds to having the states not be randomly appearing in pairs, but actually to be randomly appearing in pairs which are diametrically opposed in the circle. Okay? So in other words, each state does come with a partner, but its quasi-energy difference is pi. And so you immediately see that this is a kind of eigenstate order which only exists in periodically driven systems, because the idea of a circle and the idea of diametrically opposed only exists in periodically driven systems. Yeah. Okay, good, yeah, so I probably pushed that accidentally, yeah. Okay, thank you very much. Okay, so I'll say this again because this is the central result of this talk. So there is a second type of eigenstate order where the eigenstates live diametrically opposed in quasi-energy, and this is intrinsically a property of a driven system because the idea of a diameter only exists in a driven system. Okay, so there's a lot one could say about this, but I'd like to give you a very simple picture of how this comes about. And then I'm going to explain why, despite the existence of a simple picture, this is remarkable. Okay, so imagine you've got a system with a very simple order parameter, say an Ising order parameter, which either tells you that a compass needle points one way or it points the opposite way. And the order basically says that there's a symmetry breaking, and you choose either one or the other. And I told you the actual eigenstates are cat states, so let's call this the up and this the down state. The eigenstates are the up plus minus down cat states. And now imagine watching this compass needle over one driving period, and then you're going to see that since it's an eigenstate, the state has to come back to itself, but it can come back either after an integer number of rotations or a half-integer number of rotations. If it's an integer number of rotations, up goes to up, down goes to down, and the two states remain the same. But after a half-integer number of rotations, up and down are interchanged, and that means up and down go into plus minus up and down. So plus and minus is just a phase, e to the I pi, and the pi is the quasi-energy difference that I told you corresponded to this diametrically opposed set of states in the eigenstate order. So in other words, you would have, for the semi-classical picture, a diagnostic for the time dependence over a full period, which is that you would either have a net integer number of rotations or a net half-integer number of rotations, and this is what would tell you the difference between what we call the zero spin glass and the pi spin glass. Okay. So in other words, if you start the system not with an eigenstate but with an up state, then it's going to come back to itself either after an integer number of rotations or twice an integer number of rotations. So that's the new feature about the pi, about this new type of eigenstate order. You get period doubling, and the state comes back to itself not after a driving period, but after two driving periods. And so this is a new kind of symmetry breaking, because you don't just break the Ising symmetry here, you also break the time translational symmetry, which is only discrete. You go from having the same state after period t to the same state after period 2t. Okay? And as it breaks discrete time translational symmetry, this has been called a discrete time crystal. Okay. Now you can say, well, this is extremely boring. What I'm basically telling you, you take a magnet, you rotate it half a time in a period. Well, of course you take two periods until you come back. I mean, you could have rotated it a third of a time and you take 3 periods. So that's pretty boring. But what's very special is that this is actually an extremely robust phenomenon. So even if you change the Hamiltonian, for instance, by rotating it not by a phase, not by half a rotation, but by half a rotation minus delta, the system will actually continue to exhibit this period doubling. So even if it becomes incommensurate and would take a very long time to come back approximately to where it came from, actually it does so after every 2 periods. So this is really very robust, and it's robust against any possible perturbation to your periodically driven Hamiltonian. Okay, so that's really the central phenomenon. So let me just summarize this before I come to the experiments. Okay, and perhaps just summarize things in a slightly different language so that to give you an idea why this is such an unexpected result. So you could say, all right, we've got different symmetries, space translation, time translations. We know how to break space translation symmetries, we get crystals. So time translation is just another symmetry, why not just another symmetry breaking? Well, you can convince yourself there is a difference between space and time. So if you go 30 centimeters to the right, you can decide to go back 30 centimeters to the left and you're back to where you started from. If you go forward 5 minutes, I'm afraid you will find it's terribly hard to go backwards 5 minutes. Right? So the difference is the second law of thermodynamics, which tells you that time has a direction. Okay? And so you need a way to evade the second law of thermodynamics. So the way this connects to what I was saying earlier is if you maximize entropy in a Floquet system, you heat up and you have no correlations left. I then said if you've got many body localization, you can avoid this. And what this means is you get rid of thermalization altogether. And if you get rid of thermalization altogether, you get rid of thermodynamics and you get rid of the second law of thermodynamics. So that's the point about being localized, you no longer equilibrate. So that was the content of that. All right, so this was the ingredients: periodic driving, many-body localization to avoid the heat death, and then we got the subharmonic response of the discrete time crystal. Okay, at this point I usually get questions, but how about any of the following phenomena, which I've listed a few of them which I've been asked over time, in the course of time. So perpetuum mobile, you've probably come across. The main difference is that it's not believed to exist, so whereas this time crystal hopefully does exist. Then there are very many interesting few body systems, some of which I've listed here. The reason I wouldn't call them time crystal is because they've already got other names, like clocks, for instance. And I don't see a particular need to call them time crystal, but if you feel like calling them time crystal, that's fine. I was once even asked whether a horse isn't also a time crystal. I was not able to find out exactly why it should be. But anyway, I wanted to advertise the fact that the oldest sculpture known to mankind was that carved out of mammoth ivory. Here's a little horse, and that was dug up a few miles from where my grandmother comes from. So I'm very proud of this. Please excuse the little deviation, but I have a good reason for saying that, because I was asked whether that isn't a time crystal, and so here you go. If you ever go to Tübingen in Germany, you can actually see it in an exhibit there. Okay, so one of the nice things is that you don't have to wait 20,000 years to see what happens to this. These time crystals, and one of the cool things about many-body physics is that there are now lots of very good groups who are actually then very quickly set about actually testing this. And I've listed 4 what we call first-generation time crystal experiments, and they all look the same as far as the observations go. So they have different platforms, diamond, vacancy centers in diamond, trapped ions, and various NMR experiments. They always look the same. So basically, what you do is you have some observable, think of, say, a magnetization, like in the compass needle I showed you before. And then you drive those, not exactly at half a rotation per period, but half a rotation plus or minus delta. And then if you look at the magnetization, if you just do the driving, you see this reversal, but then the delta shows up as these beats in the envelope, okay? And so the claim then is, if you have a proper discrete time crystal, it automatically locks into period doubling. You get rid of the beats, and you just get a perfect reversal of the magnetization orientation after each step. Okay. All the traces which are published look like this, and they also all have a decaying envelope on top of them. Okay. So this tells you 2 things. So one, the interactions which are added actually do give you the period doubling as predicted, so that's extremely good news. But another thing that was then a question is, are these transient or are these long-lived signals? So of course, every signal at the end of the day is transient because the experiment only has a finite lifetime, and then the question is, does this decay because the system intrinsically has a finite lifetime or because extrinsically your experiment has a finite lifetime? And it turns out all of these first-generation experiments actually have an intrinsically finite lifetime. How much time do I have left? Okay, in that case, let me skip the transient ones and let me go to seeing these things on a quantum computer. Okay, so here's the 1-minute introduction to quantum computing. So a computer is a general purpose machine which executes, say, in a classical case, a general Boolean circuit. Okay, and the idea is that a quantum computer can do the same thing. Whichever unitary transformation you want to do, you can implement by having a sequence of quantum gates. Now, we are not there yet. Where we are is what's called NISQ devices, noisy intermediate scale quantum devices, which have 2 drawbacks. They're noisy and they're small. That's what's known as intermediate scale. And what we like to say is we should not think of these at this point in time as general purpose computation machines, but we should look at these as many-body experiments which just happen to have very long correlation times. And in that sense, they can be much better than any experimental platform that we have. And then you can ask, what do you actually need to see the discrete time crystal, which is intrinsically long-lived? And it turns out that the Sycamore computer which is developed by Google, actually ticks all the boxes. It's not optimal in the sense that it's not as big as NMR crystals, but at the same time, all the ingredients that are needed are realized in there. So what that means specifically is the following. So in the Hamiltonians we're looking at, we only have 1 and 2 spin interactions. It turns out the quantum gates which are implemented in quantum computers are exactly these 1 and 2 spin interactions. So it's a little bit, you know, XOR gates and AND gates and so on. So quantum computers have a certain gate set. And it turns out the gate sets that they have are enough to simulate exactly the Hamiltonians that we're looking at. And the gates are unitary matrices U, and the drives that we were proposing are also just sequence of unitary matrices. So basically, the setup of the processor is really ideally suited for what we'd like to do. Then you've got local control and readout. That is to say, you can feed initial states that you like, and you can read out the spatio-temporal correlations of the final state. And this is what you want to have if you want to see that there's spatio-temporal order. You want to have spatio-temporal readout capacities. And then I probably won't have time to do this. It turns out you can also do quantum parallelism, that is to say, do averaging in a single experiment, but I'll skip that. There are weaknesses, as I said before. There's finite size and finite lifetime. Okay, so we now have our phase diagram, which I'm not explaining in a lot of detail. I'm just saying we take 2 points in the phase diagram. One is in the Floquet ETH regime. The other one is in the Floquet discrete time crystal regime. And then we measure, as in the previous slides, some correlation function which oscillates. And we ask, how long do these oscillations live? And so again, we see as before, in the thermal phase, the oscillations die very quickly. And in the putative discrete time crystalline phase, they decay much more slowly, but they still decay. Now the question is this decay intrinsic because the system dies after this time, or is it extrinsic because the quantum computer is noisy? And here we use an idea which you may be familiar with from NMR experiments. This is known as an echo, but here it's a many-body echo, and it's the following idea. If I give you a unitary matrix, I can simply give you its inverse, and in that sense I can go forwards in time by evolving the system with u of t, and then backwards in time with u of minus t. If I had a perfect quantum computer, I would get back to exactly where I started from. Okay? But if I make a mistake along the way, because my quantum computer isn't perfect, I'm not going to correct it when I go back. Rather, I'm going to make more mistakes when I go back. And so what we decided to do is we're going to actually program the quantum computer to execute this, and then we're going to ask how far away from this unit matrix do we end up. And this is what's shown as the black curve here. So if the quantum computer were perfect, the black curve would be at 1. But its rate of imperfections is shown by the decay of this. And what you see in the thermal phase is that the decay of the quantum computer as a platform is much slower than the decay of the signal. And so in other words, the decay here really is intrinsic. By contrast, in the DTC, the decay of the envelope is exactly the same as the decay of the signal, so as measured, so basically the amount of errors we make is measured by the deviation away from the unit matrix. So in other words, the decay here is actually due to the imperfection of the quantum computer. And if we divide out this decay, which is extrinsic, then we get a discrete time crystalline signal, which in one case decays fast, and the other case doesn't decay for even up to 100 driving periods. So in other words, the quantum computer is bad enough to make mistakes, but it's good enough that it can measure itself how many mistakes it makes, and then you can control for that. Okay? So in other words, on this time scale which is probed here, which is hundreds of cycles, there is a long-lived discrete time crystalline signal. Of course, in an experiment like this, you never know whether it's going to survive until 10 to the 10 cycles, because there may be some process which is much slower than 100 driving periods on which it still decays. But this is the first time a trace has been seen which basically doesn't decay on hundreds of cycles like that. And so this then attracted a lot of interest from popular science people, and there's actually a rather good article in Quantum magazine entitled Eternal Change for No Energy, Time Crystal Finally Made Real. That's actually worth reading. It's a very accessible account of the history and the content, scientific content of all of this. Okay, as I mentioned, you can do quantum parallelism there, but I'm going to skip that, and I'm going to acknowledge my collaborators. So, as I say, this one's been going on for the better part of a decade. So I started working in Floquet systems with two postdocs at my institute, Arnab Das and Achilleas Latsaridis, who now hold faculty positions in India and in Britain. Then Shivaji Sondhi came on sabbatical with his graduate student Vedika Khemani. So Shivaji Sondhi was in Princeton, and he's in Oxford now, and Vedika has since become professor at Stanford. And the work together with Google was done with Matteo Ippoliti, who's a postdoc at Vedika's, and then on the Google side, the experiments were done by Xiao Mi in the group of Pedram Rushan with some theory support by Kostya. Okay, and here are some references. Okay, so Floquet thermodynamics in order. So many-body physics beyond equilibrium. The example was periodically driven systems. I've explained two ensembles to you, Floquet ETH, Floquet MBL. I've argued that ordering needs disorder because eigenstate order generalizes, but it's only present in the Floquet MBL setting. And then we've got a new system which we call the pi spin glass, a new type of order with a new type of ordering diagnostic, and this has been seen in time crystal experiments. Thanks for your attention.
Thank you very much, Roderich, for your excellent and thought-provoking talk. I want to thank you before we go into questions once again for being here. I hope you can come soon to visit us again. I also want to acknowledge at this point the support by the Maldacena program, which is due to a donation given by Juan Martín Maldacena to the Balseiro Institute. So they have also collaborated to your visit, so we also thank this program. So well, now the floor is open for questions, doubts, comments.
So can one think a bit other kind of order other than P or pi or half or other kind of order states?
Yeah. The thing is that the Ising symmetry is very simple to implement. For more complicated ones like Z5, you need parafermions, which don't have a particularly easy, simple single particle description, which is why I haven't covered this. But we certainly have constructed also 2 pi over 3 time crystals. Yeah.
Have you considered the case of open dynamics when your system is periodically driven and open? Yeah. Because in that case, it may depend on how is the coupling with the backboard, for example.
Okay, no, very good. I think it becomes easier if you do that, because basically what you're battling against is heating, in a very simple sense. If you've got an open system and you design your coupling to the outside, you can cool it again. And so you can get a steady state, and arguably this is what clocks actually do, right? I mean, you put in energy regularly, but you also take it out regularly, and the thing tells you that it's broken time translation variance, which allows you to read off the time difference since you last set it. So I think there have been a lot of publications on this topic, but I never quite understood what the conceptual difficulty is that was being removed. So really it is, in an open system, you've got a sink of entropy, and therefore you remove the fundamental obstacle to a perpetuum mobile. So, perpetuum mobiles exist if you're allowed to regularly fill in gas.
I have a short question. In the case of Sycamore, is it better to have a slower decay if you go to larger systems, so a larger amount of qubits, or smaller? Because in any case, you still have the noisy effect.
In the many-body localized phase, it's not a big deal, because it's beyond some length scale, everything's limited by the localization length, which was small. And so if we could go to much bigger systems, I don't think things would change very much. In the thermal phase, it decays very fast anyway. So actually, it turns out the finite size nature isn't that crucial. But of course, that also means, the honest second part of the answer is you can simulate that on your computer, and a classical computer, and you can also show it's stable. So
You mentioned these examples with the NV defects in diamonds. When you apply to see the symmetries, if I remember well, you have a specific ground state which is quite separated from the rest of the spectrum. So that, in some sense, you can find the symmetries if you apply excitations which are, let's say, with low amplitude or something, so as not to mix with the rest of the states.
Okay, I'm not sure I fully understand the question, but it's a general feature in Floquet systems that as condensed matter physicists, we tend to think about effective low energy Hamiltonians. And I told you, I'm looking at a system which has got a bounded Hilbert space, but strictly speaking, no Hilbert space is bounded, at least not on scales, up to the whatever size, whatever Planck constant, Planck energy. I think the statement is that in the effective descriptions of the vacancy centers, you have something which looks enough like a low symmetry spin Hamiltonian that you can do this. There are dipole interactions, so there are no continuous symmetries and so on. As such, the discrete time crystal doesn't need an exact Ising symmetry anyway, so that wouldn't be a disaster. But at the same time, since they're long-range interactions, it's actually not known what the status of that experiment is. It certainly sees a very nice pre-thermal signal, but it's not clear how to really analyze this. And since it's 3D, disordered, long-range interacting, we will not know the answer for quite a while because we have no methods which are reliable and controlled.
Well, I think it's a good point to finish, so thank you once again, Roderich Moessner.